Okay, so it's the second topic you should know in chapter 10, equation of line. Equation of line. So it's the equation of line. So it's the second topic. Let me see. It's still the topic C, and it's equation of line. In the three-dimensional coordinate system. In three-dimensional coordinate system. Yeah. But before that, because I would like to give you general result, so let's see the situation in two-dimensional case. In two-dimensional case. So first of all, let's see two-dimensional case. So in two-dimensional case, it's just xy plane. It's just xy plane. And how in xy plane, if I give in xy plane, how to get one equation, one line equation? How to get a one line equation? We know that if I give you I give you the point P, let me see, the point P0, given the point P0, x0, y0, and given the slope, I give you the slope of the line, the slope of the line. Slope of the line, and for the slope, if its slope is n, then we could design the line, right? So for example, here is x0, here we could write this way, it's our line L, the slope of the line L, and we know it passes through one point x0, y0, it passes through this point x0, y0. Here, this one. Yeah, P0 if I denote by this way. And we know if we know the slope of this line, then we could use the formula. I mean, okay, by definition is also fine. Slope, what does it mean? Slope n, it means that it's the change in y over change in x, right? Change in y over change in x. So we could denote it by this way. I mean, for any point, we denote it by p, x, y. So the change in y is y subtract y0. Change in x is x subtract x0, right? So we could multiply by x subtract x0 in both sides. We could get y subtract y0 equals n times x subtract x0. Then use this way, you could figure out the straight line passing through P0, this point. Yeah. And now we use another way to explain it. Since in three-dimensional coordinate system, we don't have the concept about slope. We don't have the concept slope. Yeah. If we want to say it's the slope of a line, we should fix one plane. But in three-dimensional case, if we have not fixed one plane, then we don't know what does slope mean. What does slope of a line mean, right? So here we use another way to explain it. So here you could see that for the slope n, it means this one, right? It means this one. But for if I consider a vector, for the straight line, if I move it in parallel, then here, and they pass through the origin. Then what can we say? Here, I want to say if I denote by the slope by b over a. For the slope, if I denote it by this way, b over a. Then for the slope, I could characterize it by this way. Here we consider the point here. Oh, sorry. Then I should explain it by this way. We consider a point AB, this way. and we consider the line, this one, and here is our here, this one. Then once you consider the slope, once you consider the delta x is exactly a, right? Delta y is exactly b. So indeed, these two, it will be better in this way. So actually you could see that if I label it O, label it by A, you could see that OA actually is they are parallel. I mean for the vector OA is parallel to any vector in L, right? OA. A, I denote the point A by this point, by this one, AB, this point. And so OA is exactly AB, right? And so for the straight line passing through O and A, its slope must be B over A. And the slope of the line L is also equal to B over A. So they have the same slope. So of course they are parallel. Right? Yeah. So in this, so what can we say? You could see that if I denote it by this way, you could see that we multiply. So we multiply by A times A x subtract x0, you will get B times x subtract x0 equals A times y subtract y0. This one. And we move it to B, move it to right hand side, and then move the scalar A to left hand side. You will get it's equal to this one. And if we denote it by T, then what can we say? We could know that we could rewrite it. It's equal to this one. First one, we know that y subtract y0 equals bt, x subtract x0 equals at. So first one is that x equals x0 plus at, y equals y0 plus bt. And here t could be it could be any real number. Here. So in this case we call it it's the parametric equation of L. It's a parametric equation of L. For a straight line L, we could characterize this straight line not in this way. The reason why we characterize this straight line in this way is that we want to consider the case in R3 space. We don't have the slope of a line. It's concept. So we want to explain it by this way. And another one is that we also could start from this one. A x subtract x0 over A equals y subtract y0 equals B. And it's called symmetric equation of L. Symmetric equation of L. This one. Yeah. So for two-dimensional case, if we have a point P0 in a straight line, and we have the slope n, then of course we could figure out its tangent line. But here, as we say, we could figure out the line passing through this point and has the slope n. But now if I give you a vector here, I give you a vector OA, the vector AB. This vector is parallel to any vector in L, and I give you a point x0, y0. Then you could see that we could write down its parallel. We could characterize this straight line in this way. We have two ways to characterize this straight line, right? Okay, and actually the vector AB, if you consider B over A, it's exactly equal to its slope, the slope of this straight line. Yeah. So in this process we use actually in this process we use the idea about two. Let me. Yeah. Actually, for this result, we also could explain it by this way here. We also could explain it by this way. As we say, given P0, S0, Y0, and a vector AB in R2, and the vector AB is parallel to any vector in L. Then how to get this one? Actually, here we explain the way in this way. We let P xy in L. Okay, and now we could see that once we consider P0P is the vector x subject x0, y subject y0, right? The point P subject the point P0. Then now you have two vectors, AB, this vector, and this vector P0P. But the vector AB is parallel to any vector in L. The vector AB, here is our vector AB, is parallel to any vector in L. It means that AB is parallel to P0P. And the two vectors, they are parallel in a plane. What can we say? Actually, it's not just in a plane. If there are two vectors in three-dimensional coordinate system, it's the same. It must be a multiple of another vector. So AB, so you know that P0P must be the some scalar t times the vector AB, So it means that so it means that x subtract x0 and it's equal to distribution, so it's AT BT, and here it means that x0 y subtract y0 equals this one, and it's exactly this one, right? It's exactly this one. Sorry, it's exactly this one. It's exactly this one. Okay? Yeah, so we could use this way to get this one. Parametric equation and symmetric equation. And so in two-dimensional case, we use this way to figure out the parametric equation and the symmetric equation for the straight line. And in three-dimensional case, it's the same. Three-dimensional case, we could use the same argument to figure out the nice equation. And I will give you examples. Okay. So there are two notation you should know. I will ask you this question. Figure out the parametric equation and figure out the symmetric equation. Parametric equation, you have the parameter. Parameter is this one, t. Parameter is this one. Yeah. And symmetric equation, then we should skip the parameter t. Symmetric equation. And for this one, symmetric equation, we will talk about it. We will talk about this one again in chapter 11. In chapter 11, we will talk about this one. Okay. So now I tell you the three-dimensional case. It will be similar. Follow the same argument. Yeah. So in three-dimensional case. So first of all, we given the point P0, so it's x0, y0, z0 in L, and we have a vector ABC, which is parallel to any vector in L. Yeah. So you could view it this way. We have a line L and a point P0, x0, y0, z0. And we have a vector, given a vector ABC, a vector if you call it V. And it's parallel to any vector in L. Any vector in L, it must be this one, this one, this one, or this one. It should be any vector. It must be of the form, right? It must have the same direction. It must have the same direction. But of course, they could have different lengths. Anyway, if they are parallel, means that V must be of those. They must have the same direction. They must have the same direction. So it's our V. It's ABC. It's our ABC. So now we could label any point P, X, Y, G in the line L. So let P, X, Y, G in any point in L, be any point in L. And then now we know that P0P, they must be parallel. It must be parallel to V. These two vectors are parallel. So these two vectors are parallel means that one vector is a multiple of another vector. One vector is another multiple of another vector. So P0P is equal to T times V. T times V. So P0P is P0P, P subtract P0. So it's X subtract X0, Y subtract Y0, G subtract G0 equal to T times V. The vector V is this one, ABC, right? And distribution you will get AT, BT, CT, right? AT, BT, CT, this one. And now check H10. Oh, sorry, it should be the first coordinate, second coordinate, the last coordinate, the third coordinate. So you will get the same result, right? Here is the same result, so we could write it down. And we still have the name, so I just keep the name. So we keep the name. So how we will get is X subtract XT, 0 equals AT, Y subtract Y0 equals BT, G subtract G0 equals CT. So parametric equation of L means that it's X equals X0 plus AT, Y equals Y0 plus BT, G equals G0 plus CT. This one is called parametric equation of L. And sometimes the parameter T we could skip it. Yeah, T could be any real number. And symmetric equation, then we for this result we move the value the number A to left hand side, so you will get here. So from these three equations you will get AX subtract X0 equals all of them equals T, right? All of them equals T. So symmetric equation, then we skip the equation T. So we just have this one. X subtract X0, Y subtract Y0, G subtract G0, ABC. Yeah. Okay. And by the way, for the symmetric equation, if some scalar A or B or C equals 0, for example, X subtract X0 equals 0, then you will get X equals X0. So in this equation, we don't have this 10, but you should write down this one, X equals X0. You should write down this one, okay? Just to remind you, yeah. Okay, so it's called parametric equation, symmetric equation of the line in three-dimensional coordinate system. So now let me consider the concrete examples. Yeah, so in this chapter you should know how to figure out a plane passing through 3 points, and you should figure out in three-dimensional coordinate system. If I give you two points in a line in a straight line, you should figure out the straight line passing through 2 points, and they are related. So now let me tell you how to see that. It's second question you should know in this chapter. So you want to find parametric equation and symmetry equation of the line through 2 points A 2, 4, negative 3, B 3, negative 1, 1 through these 2 points. Okay, so now let's see how to solve it. Yeah, so now we have point A 2, 4, negative 3, point B, sorry, the point AB, 3, negative 1, 1. Yeah, so the straight line pass through these 2 points. So yeah, so in our previous, in this result, you should know we should have a vector in the plane, in the straight line. So we could consider the straight line AB, right? So it becomes 3 subtract 2, negative 1 subtract 4, 1 subtract negative 3. So it's 1, negative 5, 4. This vector 1, negative 5, 4. So we have a vector. This one. And here we know that if here we denote by A 2, 4, negative 3. So if we let P be any point x0, x, y, z in the line L, then we know that AP, this vector it's parallel to AB. They are parallel. So AP is equal to T times AB. Yeah, so we have this one. Right? So we have this one. So indeed, you could see that AP and our AB is this one. Here is our B. B is 3, negative 1, 1. So AP, let P be the point. P is the point x, y, z, so it's x subtract 2, y subtract 4, z subtract negative 3. It's equal to T times 1, negative 5, 4. So you could see that it's T, negative 5T, 4T, and G plus 3. So you will get x subtract 2 equals T, y subtract 4 equals negative 5T, G plus 3 equals 4T. Yeah, so for the parametric equation, it's exactly this one. X equals 2 plus T, y equals 4 subtract 5T, G equals negative 3 plus 4T. It's a parametric equation. Of error. Yeah. And for the symmetry equation, just for this equation, for these 3 equations, we just here you could see that x subtract 2, the coefficient is 1 times t, so we divide by 1, so we could write in this way. And here its coefficient is negative 5, so we divide by negative 5. So y subtract 4 divided by negative 5. And g plus 3 divided by 4. And all of them are equal to t, right? But this term if we say symmetry equation, we should skip it. Symmetry equation of error. We should skip it. So it's a black form. For its symmetry equation, it's a black form. And actually, if you see, for its denominator, 1 negative 5, 4. 1 negative 5, 4 is exactly this one. The vector AB, 1 negative 5, 4. Just put it in the denominator, it's fine. Then subtract the point x0, y0. Subtract the point, I fix A, right? So it's our x0, y0, z0. So it's exactly x subtract x0, y subtract y0, z subtract z subtract z0. This one. Yeah. So for a straight line pass through 2 points and a plane passing through 3 points, for these two results, you should know how to solve it in chapter 10. Okay.